Hello, I'm Brett Bibby. Thanks for joining me today to learn about an interesting and important subject. Let's get started. Today, we're going to look at the growing inefficiencies in software applications, what the causes are, and what you can do about it for the betterment of Earth and the lives of current and future generations that live here. For context, I've been making video games and its related technology for my entire career. Now, video games have been pushing the limits of what's possible with technology since the very first computers came into existence. And today, the video game industry is bigger than movies, music, and books combined. We've learned a lot about efficient computing, historically to make more interesting and richer experiences, but this know-how is also beneficial for general computing too. And that means we can leverage this know-how to make high-performance, yet more energy-efficient applications. I have the good fortune of working at Unity, whose technology powers the majority of games in the world. Our tools let people easily create real-time 3D experiences, and create they have. By way of example, more than 70% of the top 1,000 mobile games are made with Unity. And creators find success wherever their audience is because we support more than 20 platforms. That wide reach has resulted in Unity-based apps getting installed an incredible 5 billion times a month. Now, this is important and relevant because today I want to share some of the key insights gained from this broad reach and understanding. Let's start with the destination of these creations, screens. Now, when we look at screen sizes in terms of pixels, we can see dramatic growth in pixel density on screens over time. Many people grew up watching analog television broadcasts. TV broadcasts into your home via antennas. And then came high-definition television and the start of a truly digital future. Incredibly, some tablets have already surpassed that with handheld high-density displays. And today, you can go to the store and buy a 4K ultra high-definition television and play games at that resolution. Now that's 108 times more pixels on screen in that ultra high-definition display than the standard definition television. And while this is from a television perspective, there has also been generations of standalone gaming consoles. In fact, ARM has powered consoles like Nintendo's for decades. Examples include the 2001 Game Boy Advance, the 2011 Nintendo 3DS, and the current Nintendo Switch. In addition to the screen size, the amount of content that creators put on the screen and the processing behind each one of those pixels has also increased dramatically. Many can remember playing Doom when they were younger. It had this huge, tall, full-width health bar at the bottom to reduce the number of pixels it needed drawing each frame. Now, Doom was a groundbreaking game for its time in so many ways. When we got to high-definition resolution, games had enough pixels and enough objects to work with that they were able to create an incredible number of immersive experiences. High-definition gaming helped drive CPU and GPU technology forward, with consumers acquiring the latest hardware and devices in order to play the latest games. Shown here is a recent screenshot from the game Naraka. And device makers have made huge strides in innovation and have increased the pixel density while decreasing the form factor, making the pixels visibly disappear. More powerful hardware enables even portable devices to have high-quality rendering and effects in real time. And this allows more complex and realistic experiences to be possible. Pictured here is Call of Duty Mobile running on a recent Android tablet. And now we're at a place where nothing is beyond the reach. Combining intricate detail with physically based rendering techniques on ultra-high definition displays brings a new level of immersiveness to these experiences. Pictured here is one of our internal projects called Megacity, and it has hundreds of thousands of highly detailed objects and unique audio sources all running interactively in real time. Now let's look under the hood to understand what's going on with the underlying hardware. Now, this is a bit of an eye chart at first glance, but this graph shows the microprocessor trends for the past 48 years. What it really shows is, starting at the top here, we can see that the ability to put ever more transistors into service in microprocessors has been steadily increasing. But that's been getting diminishing returns in our ability to use it. And this is largely due to physics. And putting more cores to work, using more power, has been the common solution lately. But it's hard to efficiently use multiple cores at the same time for developers in practice. Now, this gives us a strong clue where the problem actually lies and what we can do about it. And perhaps more at issue is the growing amount of memory being used for content and its data, as you saw in the earlier game examples. Now, let's take a look more closely as to why. To understand performance, you have to understand the hardware. In this simplified example, we have some data in memory here on the right, and we want to work with it. So we fetch it from memory and load it into the CPU. Now that we have it cached and local to the CPU, we do some work with it. In this case, we're just going to add two numbers together. And then finally, we store the results of the cache back out into memory. Now this sounds simple enough, but the chips are wired together into a large city of interconnected circuits. And because it's electricity, only one car can move around this circuit city at a time. This means that there is a large choke point on moving things into and out of memory. In fact, the biggest bottlenecks is in load store operations to memory. The caches help create locality of data, but only if the data needed is in the cache. In a study by Google, they found that more than 60% of energy was being used to move data around, and only a minority was being used to actually transform the data. In our signal-to-noise ratio here, we have too little data we need and too much data we don't need. Seems easy enough to fix. Let's just organize the data better. And you're right. That's what we need to do. But most people delegate that task to their languages and its compilers. Your device speaks machine language, you speak human. And computer languages were invented as a compromise between humans and machines. Your compiler takes the abstract language you wrote and generates the commands that will transform that data over time. The problem is expressing how you think about the problem in a way that can be implemented by machines. A common type of language is one that is object-oriented. Here we have different objects represented at runtime as different clusters of colored boxes. You can see I have 4 objects of the same type outlined here in white. When we work with an object-oriented language, it fetches the object and its surrounding data into the cache to work with. As I iterate over the objects, in this case 4, it will likely need to load and save it 4 separate times because technically the objects are likely farther than what we call a cache line apart in memory. Now this is wasteful of power, time, and it makes multi-threaded programs much harder to implement in general. Conversely, data-oriented design organizes data into tightly packed arrays by system and type. Here, we can see by box colors that group similar types of data together into an array. And here is one system array we want to work with. Now, when we transform the data, we work system by system, fetching packed arrays of data. And because the systems are fetching different arrays, it actually makes multi-threaded programs much easier to implement. And it's also more efficient. Taking a step back to look at the overall system, it's a logically oriented city of circuits, so to speak. Transistors are clustered together to form circuits that are then assembled into logical blocks that form an interconnected system that operates on data. If you try to process chaotically disorganized data on an otherwise organized system, many of the capabilities and resources of the device will go unused, which isn't as efficient overall. Now, staying with the city analogy, imagine a large city filled with streetlights and traffic signals everywhere, but there's actually only people and traffic in one neighborhood. That's a lot of wasted energy across the city in streetlights and traffic signals nobody's using. Meanwhile, in that neighborhood, it's a chaotic traffic jam and crowded where everybody's at. Ideally, you want to do as much work as you can simultaneously across your device. Then shut it down, suspend, sleep till the next round of processing is needed. Now, logically oriented data enables more of the computing resources to be put into action at once, completing faster and therefore maximizing energy use over a minimized amount of time. There are many ways to approach solving this. At Unity, we've created DOTS. DOTS is an acronym for Data-Oriented Technology Stack. Now, DOTS consists of three primary parts that together form the foundation for high-performance data-oriented computing. The first is the Entity Component System, ECS. Now, this is a system that allows developers a way to specify the data, how it's accessed, define a system to process the data, and then manage the objects, dependencies, and interactions associated with it. Second is a C# job system, and this makes writing multitasking, multi-threaded programs much easier, straightforward, and error-proof. And it does that by detecting problems with the program during compilation. And finally, we have the Burst compiler. Now, Burst generates high-performance vectorized code, commonly known as SIMD. Now, SIMD stands for Single Instruction, Multiple Data. SIMD processors are some of the most powerful yet least used resources in CPUs. They are default parallel nature because just like the acronym says, it takes a single instruction and applies that to data that is sitting in parallel pipelines. Now, ARM's SIMD technology is called Neon. In collaboration with our partners at ARM, we added ARM Neon hardware intrinsics to our Burst compiler. Now, this results in up to 10x performance uplift for things like graphics, machine learning, and physics workloads where you're going to be processing many objects at scale continuously. Great example of this would be like axis-aligned bounding boxes or radius-based collisions. Now, this means that developers can do more per frame as well as consume much less energy when doing the same work. Whether you use Unity's DOTS or you start down this path all on your own, I'd like to cover some tips we've learned putting data-oriented technology into practice. The first tip is to get into the habit of doing everything in batches, even if it's a batch of one. The temptation of doing things one by one always creeps back into designs. One way to illustrate the problem is with a bread making machine. If all you wanted to do is make a single loaf of bread at a time, bread machine is a great choice. It hides the process from beginning to end behind a convenient interface. Press a few buttons, set the weight, cooking time, and you're done. If you want to make 2 loaves of bread at the same time, you might consider 2 machines, or maybe 3, and so on. But there's a point where the overhead of all these machines will outgrow the benefits of using them. Data-oriented design is all about breaking up that process, having a machine that makes dough all at once, a machine that makes all the loaves at once, and another that bakes them all at once. Once you get into the habit of thinking this way, things become easier and actually make more sense. Second tip is that you need to design for scale all the time. The common wisdom of premature optimization being evil doesn't imply ignoring performance is a good idea either. It's important to anticipate how something will scale, how its performance might degrade over time as a consequence. Testing things at scale early on and adjusting the design accordingly is important. The risk of ending up stuck with an inflexible design actively resists optimization, and that risk is very high and also very common. This can also be illustrated by the previous example of a bread making machine. If you'd reached a point where you invested in a lot of these machines and you notice that you cannot scale any further, a complete refactoring of your bread making process will be expensive and time consuming. Finally, resist abstraction. Abstraction often happens because it feels right and that approach seems deeply ingrained in computer science education. To illustrate this with an example, consider a traffic simulation that deals with a lot of cars. But about 1 car in 1,000 is pulling a trailer. Now, some programmers will tend to implement this in such a way that having a trailer is a property of any car. And the things a car can do in the simulation will then have to deal with the eventual presence of a trailer. In practice, a better approach might simply be to consider the car with trailer configuration to be special and unique, requiring a special interface with dedicated code and leveraging the fact that they are rather infrequent. This is one way of interpreting the data-oriented design principles, of making the cost proportional to the frequency of occurrence. And this also goes to the core of decades of thinking that have led us into a performance and efficiency quandary. Instead of hiding, abstracting, and encapsulating our data, we need to do the opposite and lead with data, its specification, and make sure that it remains with high integrity. Fortunately, there's a lot of database know-how to be found within enterprises that can help us in this transition. If you're new to the concept of data-oriented design and how compilers and system works, this can be a lot to take in. To start your journey on this road to data orientation, I suggest you check out these sources. You can head over to Unity's page on the subject, or you can just Google data-oriented design to get started. Some of you may want to dig deeper by looking at one of the talks shown here as well. So, this sounds great, but what's the payoff of this new way of thinking? Well, in games and intensive real-time applications, and the world is going more real-time, the payoff is usually huge. A simple example of 10,000 objects moving very simply in a classic C# object-oriented implementation in our own tools took 6.14 milliseconds. And that's already an optimized game engine. When we use dots, that same implementation took just 0.11 milliseconds. That's 55 times faster, not 55% faster. Some games have millions of players. Imagine if a game with 1 million players, where each player is playing for an average of only 10 minutes per day, used an optimization like this one single one that I'm calling out. That would save more than 6 years of CPU time per day. I've talked a lot about games, 3D and real-time, so I also wanted to give you a completely different type of example, this one from Facebook. Now, Facebook looked at optimizing strings in their internal libraries used across their organization, and they achieved a 1% performance improvement, which is a lot considering how foundational strings are, text is, to Facebook's platform. Let's hear from them what the impact of that was.
But this 1% is 1% across all of Facebook. This 1% doesn't just apply to the compiler. This 1% applies to every single C++ program that Facebook runs. This is really, really good for us.
I think this video clip does a good job emphasizing how big of a win this was for them. Now, the most important example, though, is yours. To date, the total deployment of ARM-based chips is more than 200 billion units. The number of ARM-based chips shipped continues to accelerate, with more than 100 billion devices shipped in the past 5 years. At the current rate, 100% of the world's shared data will soon be processed on ARM, either at the endpoint, in the data networks, or the cloud. Now, ARM technologies reach 70% of the global population. Your investment in development time is a fraction of the usage time by end users and consumers. In my simple example, we could save more than 6 years of CPU time and power per day. What could you save? What would be the impact of efficient data-oriented computing over a decade of use by billions of people? Imagine the impact your choices can make. And when we all make these choices, it completely changes the world for current and future generations. Thank you so much for your time. I do hope you found this talk both informative and provocative. Thank you for doing your part to save our amazing planet. Have a great conference and a wonderful day ahead.